Hey, welcome back to Gold's Garage. This is the third video in a series about the repair of this pretty unique 350 cubic inch engine that I've got here. And I started off, we decided to show, this isn't actually a build up from scratch, it's a repair job and an engine that I didn't build. And so two short videos that I published on this engine already, and over 150 comments. And having a YouTube channel is like having access to worldwide consulting service of guys and girls that are willing to share their knowledge and experience. And based on the comments, some of those 150 comments, we're actually going to change the plan in terms of how we're going to repair this. So I've got lots to talk to you about. I think Robert made a comment, you don't have enough information to make a decision, and he's right. So I got more information. Every engine has a story, and this one certainly has too. I've also talked to my customer as a follow-up, and that's kind of changed my thinking as well. So I'm going to share all that with you today. So first of all, just to get this out of the way, I mentioned that this engine had been in a Corvette. I don't know, it might have been. It's a 19. I checked the code on the deck of the block, CKB, and that is, this engine came out of a 1972 Camaro, 350 cubic inch, 170 horsepower, two-barrel engine with an automatic transmission. That's how it was born. It's an O&O block. But those O&O blocks were basically from 69 to 79, and this is not a 4-bolt main block. Some of them were. The 4-bolt main blocks went in Corvettes and Z28s, I think, for the most part, and maybe trucks too. But it's an O&O block. So here's something unique. I just rechecked it because I couldn't believe it. With my dial bore gauge, and as accurate as I can get, and I always am, the standard bore, according to the manual for this engine, for the bore spec, the standard bore, never been bored, is 39995, half a thou under, to 40025, 2.5 thous over. And it's in spec. I just checked them again, just to make sure. The range is 1 to 2 thou over. So in other words, in spec, 401 to 402. So how the heck does that, where's this engine been for 50 years that it's not worn out? I mean, that's amazing. And it's been in a hot rod. A customer, Paul, has an S10, which is a 2,400 pound car. And, it looks like Paul's been pounding on it pretty good. And I talked about that before. So analysis, one comment Robert stated, you don't have enough information to decide what to do, and you need to get more. So I went back and talked to Paul, my customer, and tried to figure out what happened. And initially, when I talked about this engine, I just made a guess, probably he has 10.5 to 1 compression. Well, I should have taken a closer look at that. Since I did, the block is not decked, and the head gaskets that they use were the standard Felpro 40 thou compressed gaskets. So that gives you a quench of 70 thou. That's going to raise a red flag right there. And with a 4-inch bore and a 64 cc combustion chamber, that's less than 9.5 to 1 compression. So I was wrong there. And a lot of guys, guess detonation, and based on the fact it's got cast iron heads, 10.5 to 1 compression, and the fact that if you haven't watched the first two videos, I've got a rag here, so take that away. If you can see that the top half of all the rod bearings and the bottom half of all the main bearings, the copper is actually showing. And so how does that happen? That's a compressive force pushing down on the piston, basically trying to compress the connecting rod and push the crankshaft out of the bottom of the block. So the bottom half of the main bearing is also, the copper is also showing. Those are compressive forces. And certainly that makes detonation would be an explanation for that, because if you have detonation, and if you have a lot of quench, then you got a lot of force trying to push that piston back down. The dynamic forces of multiple combustions going on in the combustion chamber at the same time, and that's what causes compressive forces. However, that's less of a factor with 9.5 to 1 compression ratio, so you wouldn't expect that. So I talked to Paul this morning based on all the comments, and something I didn't know. He told me that he did have an issue with the engine running on when he shut it off. Now, back in the 70s when they first lowered compression ratios and they were using very little timing advance and all that stuff, I had a 75 Monte Carlo 350, just a stock engine, and it was common if you shut it off it would continue to run. How does that happen? Well, that may be part of the explanation of what's happening to this engine, because there's the top of a piston. Hopefully you can see that in the camera, I hope. Covered in carbon, and the combustion chambers and the cylinder heads are also covered in carbon. A lot of it collecting right around the exhaust valve, and that's a clue that maybe we've been looking at the wrong thing. So what happened to those engines, even though they didn't have high compression, and if they're running on when the ignition shut off, then that's not pre-ignition, right? But it's not pre-ignition from the spark plug, but you got ignition going on. It's basically, I'll describe it as dieseling. The piston's coming up, it's compressing fast, the temperature of the engine is hot. I don't know what the rubber temperature was in Paul's experience, but usually you got high temperatures, the piston is rising, the compression is rising, and when the engine gets hot enough, that carbon will glow red and basically cause ignition. You got a combustible mixture in there, and that is pre-ignition, where you have ignition going on before the spark plug even fires, if that explanation makes sense. So that's one of my theories now, and that's a new revelation, and the product of so many comments, 150 or so or more comments, talking to my customer, and so that explains a lot. And so that would also put all the forces on compressive forces, trying to compress the connecting rod, trying to push the crankshaft into the oil pan, essentially. So what's the other mode of failure, and what are the other, if you had even wear around, the other way engines fail is from high RPM, and that's a different kind of a scenario. And in my experience, and some of them that I built, circle track engines fail not when your foot's on the gas, but when you lift. How does that happen? Okay, so those forces are in the other direction. When you lift, you're at the highest RPM, so the piston is coming to the top of the cylinder. It wants to keep on going. It doesn't want to change directions almost instantaneously. It wants to keep on going. You close the throttle, you got maximum RPM, and you close the throttle, you create a huge suction that's trying to pull the top off the piston, okay? And that's how engines fail from high RPM. And what's the difference is, the forces may not be greater than detonation, but the connecting rod is stronger in compression than it is in tension, number one. And when it's in compression, the connecting rod bolts are not a factor because they're not loaded when it's in compression. But when they're in tension, when the piston's going to the top, they definitely are loaded. So that's the other mode of failure. That's not this mode. My thinking now, and I'm looking for more comments from guys that have been helping me out with this, that the carbon, not high compression carbon, a lot of carbon on top of all the pistons. Once again, detonation, that we would think if you had what's going on there is multiple combustions going on in the cylinder because of improper quench or whatever, improper mixture. You would see some spalling on the top of the piston, evidence of damage, but the piston is totally covered in carbon, and in fact it's even wet with carbon. on the exhaust side. So my thinking right now is that's probably what caused the damage. Now, I don't know how this engine was tuned or anything. I never saw it in the car. I never even seen the car. So that covers that off. So throw that out for you. So the other thing is I started off saying that I was going to try and make this what I call a surgical repair. Just do enough to fix the problem. And if maybe it goes back to my sort of corporate experience, I managed maintenance in a steel mill. Costs and downtime and all that's a factor. You usually do no more or less than you have to fix the problem. And that was kind of the approach I took, and I understood from my discussion with Paul that, you know, budget was a factor. Well, I've talked to him this morning, and basically he's told me, you do whatever you have to do. I want that engine to be good and last forever and not have to worry about it. If you have to do more, do more. So the plan before today was, I had ordered a new crankshaft, new connecting rods. I intended to take these pistons to my machine shop, atch the machine, and have them press the pins out so I could reuse them, get the rods off them, press the pins out, and then I was going to clean them up and reuse them with new connecting rods and crankshafts. So right now we are looking at, instead of doing that, buying a complete rotating assembly. Don't have to go to the machine shop at all for that now, and it'll be a match set, and obviously there's other advantages. A little more cost. So the other thing is, I think I've mentioned already, the bores in this engine are still in spec, so it gives me the choice. I could still use hyper-eutectic piston or a forged piston. So I haven't talked. Barry at Performance Unlimited is providing all the parts for this job. It's the weekend, so I won't get to talk to him until tomorrow, and we'll see where that goes. So thanks, guys, for all your comments, and for those that have been following this, that's where it's at. Every engine has a story. Every engine is a science project, whether you want it to be or not. Sometimes you just want to get the work done, but couple other things that came up in the discussion in the comments. These TRW Pistons. So I haven't seen these pistons for a long time. In fact, I had a hard time researching the numbers. The number on the piston is TRW 7064. TRW back in the 70s, by the way, before we had all these aftermarket stuff come out, was, I think there was a subsidiary of GM actually originally. I'm pretty sure that's true. They were definitely a major supplier to GM at least. And so my drag racing car had TRW pistons in it, for example, modified production car. So 12.5 to 1 compression, but basically they looked similar. So 7064, so Mike found the research. They are equivalent to TRW L2417F, and that they are a forged piston. And I was pretty sure they look like that, but they are a forged piston, and they are no longer made, and so that's not an issue anymore. So, okay, the only other thing I wanted to kind of mention, and if you don't want to hear an old car story, you can turn it off right now. But I got an old car story. This reminds me of one because I quit drag racing in the 70s and later eventually got into circle track racing, but I had another 68 Camaro in 1973 or whatever, C-modified production car, and it had TRW pistons. That's what reminded me of this. They were 12.5 to 1. And during the summer, I used 3 different camshafts. The one I started off with, and I changed the camshaft twice. And you change the camshaft one week, and then you got to change the gears the next week to catch up to the camshaft because you're going high RPM. So every time we did that, of course, you went to more lift, and more lift meant less piston to valve clearance. So how do you fix that? With the engine still in the car, what we actually did was took one valve out at a time. We had a cutter, an intake and exhaust valve with a cutter on it. Put that cutter in where the valve was, put the head back on, use the drill, and increase the piston to valve clearance. I don't know if there's lots of guys watching this channel that are kind of from my era, 60s, 70s, and I don't know if you can relate to that, or that sounds pretty crazy, I guess, but it'd be a horror story to do that today. I certainly wouldn't try it. But you know what? Uh, it worked. We changed camshafts 3 times really, if you include the first time, and every time we did that, it went a little faster. Not a lot, but when you're drag racing, a little is important, right? So anyway, just sharing that car story with you. One other thing, I got this out here to remind me. This is a dual quad breather for the 409. I've talked about the 409 before, if you're interested in that. So here's where that's at. My buddy at Bob Atchison actually has a block. It's a very expensive block. And we have, my customer, I moved it over to the other side of the shop now, has all the rest of the important parts. The 690 heads, the dual quad intake manifold, the Carter AFB carburetors, the dual point distributor. We have everything to build a correct 1962 Chev 409. If someone's interested, the issue is that it's an expensive build, so my customer doesn't want to do it on spec, but if someone's interested in it, and we even have the correct air, what's that worth, right? The correct air breather for it. It could be built right to, specs for numbers matching 62 bubble top or whatever. It doesn't have to be bubble top, but if anybody's interested in that, let me know. We have everything we need, but it's quite an investment. They're definitely valuable, but there's not a customer coming around every day for one, obviously, so we're not going to do it on spec. Hope you found that interesting. I always forget to say please like and subscribe, but obviously we're almost at 20,000 subscribers, and that's like having 20,000 consultants giving me information and helping me out. Appreciate that very much. We will hit that milestone sometime this week. Thanks to my support team, Mike Kimball, Alex Vendrig, even though he's on vacation right now, my son Michael. We're doing good, we're having fun and sharing our experience, and I'm glad you appreciate it. Thank you for watching Gold's Garage.